So I've received a couple questions now about the kind of data that the detectors produce and what we look for and how we read that data, and also about the precision and computing power of these detectors. So I decided to dive into that a little bit. Just as a recap, we're talking about the scintillation detectors that use a scintillator crystal like this one to capture the energy from some energized particles like gamma ray photons or energized particles from the atmosphere and convert that energy into visible light, which we can then work with and measure. And these detectors run on the same basic principle pretty much for all of them. And once that light is produced from the crystals, it then goes on to the next part, which is called the photomultiplier tube. And essentially this thing is like a reverse flashlight, and this is one that has actually had the glass shell removed. Normally these are encased in glass and kept under a vacuum inside of the glass. But starting at the bottom, there will be a material which, when the light from the scintillator crystal hits it, emits a few electrons. And then those electrons, because this is held at a high voltage, essentially get sucked up like a vacuum through this system. And each of these copper wings that you see here, or levels, every time the electrons hit one of those, they produce more electrons, which then get accelerated even more. And then this cascade of electrons multiplies and multiplies until we have a massively amplified signal. These essentially go from a few electrons in the beginning to having enough electrons to actually form a measurable electric current at this end. These parts that actually do the amplification are called the diodes, and each of these pins, some of them go down to a diode and provide them with the high voltage that is necessary for the acceleration and amplification process. And then the rest of these pins actually read out the data from the end of this. So once the electrons have been amplified and accelerated, they reach the end, and then they travel through one of these pins or some of these pins and are read out by some more electronics that go here on the end and attach to the pin. So in its simplest form, that's really all it is. It is a crystal which traps some of the energy from the original particle and converts that into light. And then that light hits the photomultiplier tube, or the PMT, which then converts that light into electrons, amplifies those electrons into a big enough signal so that we can measure it with simple electronics. But then that begs the question that we started with: what do we do with that signal once we have it, and how do we read that signal? Well, we start by asking, what are we looking for? We're looking to know when the detector detects a particle, right? So we will have some baseline signal with noise, and then we should see some sort of spikes or some sort of sign that we are detecting a particle. And how do we read that signal? We measure the signal by using one of these. This is a digital oscilloscope. These are ubiquitous in the scientific community, particularly in physics and electrical engineering. And anytime you see a science fiction movie or a movie that's displaying science, you will always see some sort of oscilloscope looking device with some analog signal displayed on the screen. And these devices allow us to look at a raw analog signal, which comes in through one of these inputs, and then it graphs this signal on an axis where the x-axis is time and the vertical y-axis is voltage. So we can use the knobs on the oscilloscope to zoom in and out in the time axis and in the voltage axis to the size that we think the peaks may be for that detector and these particles. And then if we see peaks, then we know that a particle has hit the crystal, created light, and that light has been transferred into electrons, which are then amplified into a signal that we can see. So if there are no particles hitting the detector, we expect to see something like this, where we have our time on the horizontal, voltage in the vertical, and we see just this fuzzy line of nothing in the middle, just pure noise in our signal. Whereas if we do see a particle, then we see something like this, where we have our flat, noisy signal, and then at the instant that the particle was detected, we see this huge spike that goes up very quickly, and then we see this exponential decay that goes out from that due to the electronics within the detector, and then it eventually returns to ground and we see no more signal again. On whatever count rate of particles we have, or how often particles are hitting the detector, we would see peaks every time we see a particle. So if you have a very high or very fast count rate, then that would mean that you would have peaks almost all the time, sometimes even bunched on top of each other. But then that begs the question, how do we look at this peak and gather anything from that? It just looks like a spike on a graph. Well, if we see a peak that looks like this, then we can see the height of this peak here. And this is measured in volts because the vertical axis of the oscilloscope is voltage. But because of the way that the detector is built, we know that the voltage of this output signal is directly related to the energy of the particle that came into the detector and made this peak. So if we know the voltage, we can immediately figure out what the energy of that peak was. And additionally, we can look at this peak, and by measuring how long it takes the peak to go from the top back down to the original noisy signal, we can measure the time of that peak. And so now that we're talking about the energy and the time of the peak, that brings us into our conversation about the precision of these detectors and crystals, and how precise can we really get with these tools. When we're evaluating the type of crystal scintillator that we use, we look at two main parameters, and those are two different kinds of precisions that the crystal will have based on its inherent qualities. And these are energy resolution and timing resolution. If we think about resolution in the sense that we are familiar with it, you may think of looking at a picture, and the resolution of the picture would be directly related to how many pixels are in the picture and how much detail you actually have in the picture when you zoom in. And the resolution can tell you how far you can zoom in before it will start to get blurry and you'll start to notice those individual pixels. So in a similar way, when we think about energy resolution, what that really means is how much can we zoom into the energy scale of this peak before we start to lose information and get fuzzy. And this doesn't just have to do with the qualities of the crystal. Any crystal will have specific characteristics that make it more or less energy precise, but also if we want to have a high level of energy precision, then we need to also make sure that our electronics, like our photomultiplier tube, is also developed for high energy resolution. That means none of the electronic processes that are happening in there during the amplification mess up the information that we have originally from the crystal about the energy of the incoming particle. And we also have to make sure that our data collection and analysis techniques retain that information as well and don't mess anything up or blur the image in any way. And then we have timing resolution. And similar to energy resolution, this just means how closely can we zoom in on that horizontal time axis and still be able to clearly see what's going on. So imagine this. I want to know if two events happened at the exact same time or if they happened one after the other. But the events themselves were separated by 10 nanoseconds. So in order to determine if they happened at the same time or one after the other, I would need a detector that is capable of seeing nanosecond timescales. If my detector is not that precise in the time regime, then all I will see are two events that are blurred and seem like they are on top of one another. But if my detector is sharp enough, then I can zoom in as far as I need to on the horizontal axis, and I can see that there actually is a few nanoseconds of space between them. And that is why we care about these time and energy resolutions, because if we're doing an experiment in which we need to know that things happen at the exact same time very precisely, or if we need to measure very precisely the energies of particles that we detect, then we want detectors that are able to measure those energies and those times as precisely as possible. And so we will spend a lot of money and spend a lot of time in testing and characterizing these detectors to make sure that we know without a shadow of a doubt that we can trust their energy measurements and their time measurements. And we can actually do measurements to quantify both of these resolutions. So take, for example, the energy resolution. Imagine this. We have this particle that we are detecting coming into our detector over and over, and we want to know the energy of that particle. We know that this particle is always the same and it always carries a specific amount of energy, but we want to know how well our detector can actually measure that energy. So what we do is we develop a data acquisition system which takes in these peaks and measures the height of every peak that it detects, or it measures the energy of the peaks. If the energy resolution of the detector is good, then it will be very good at measuring that height and that energy. And it will give us a reliable energy every time that we measure that particle that is very close to the same amount of energy that is actually in the particle. But if it's bad at measuring the energy and has a bad energy resolution, then it will give us wildly different answers for the energy every time we measure that particle. So we'll have a wider distribution of energies, even though the original particle had the same amount of energy every time. So what we do is we run this experiment and then we count over thousands or millions of these times of measuring this particle. And every time we measure an energy of a peak, we put it on a histogram. And a histogram is just a plot that measures how many times you count a specific amount of energy. So in these two histograms, we have energy on the x-axis and the number of times we measure that energy on the y-axis. So here, this would be an example of a detector with a good energy resolution. We see almost no energy counts for most energies except for the one specific energy of the particle that we were measuring. And at that point, it spikes. So almost every time the detector is measuring that specific energy. Whereas for a detector with a bad energy resolution, it seems as if this peak is spread out or blurred across the distribution of energy values. And this is the same process that we do all the time to characterize our detectors and or get to know them. So what does this tell us as researchers? If we have an experiment where we really want to know the energy and we make sure that it's reliable, then we need to pick a scintillator that has a very good energy resolution. An example of that would be a pure germanium detector. Germanium detectors are known for having a very high degree of energy resolution, so that you can pick out exactly what isotopes within a sample are responsible for the radiations that we are measuring. Or if you want to have a very good timing resolution, say you have an experiment where you want to measure things that both happen in two detectors at the exact same time. We call that a coincidence measurement. Then you need a detector that can very accurately measure the timing of those two occurrences and then see if they have the same or different timings. So in that case, you might decide to go with a barium fluoride crystal for your detector. Barium fluoride is a very rare, very expensive crystal material, which we use in experiments which require a very high degree of timing resolution. The process of scintillation that happens in this crystal, which takes some of the energy from the energized particle and turns it into visible light, that process happens very fast in here, to the point that the peaks have time widths less than nanoseconds, sub-nanosecond time scales here. This is to the point that the limiting factor is not our crystal, it's our electronics. It is hard to invent electronics that can keep that measurement so quick to preserve the timing resolution that we get from the crystal, to make sure that we don't lose that resolution as it goes through the PMT. And yes, this is one of the crystals that I cleaned in my original TikTok. So if you want to see me getting this crystal clean, which is already a little bit dirty, and cleaning a bunch of other these crystals, then yeah, go check that out. So then that begs the question, if we don't want to lose any of that timing information that we get from the crystal, and we buy super expensive electronics to make sure we don't lose that information, how do we take in all of that data to make sure that we can collect the entire peak and not miss any data points if it's happening so fast? Think about that. If I wanted to take an hour's worth of data, but in order to get all the information I needed, I had to take a data point every half a nanosecond. Think about how many data points would add up over the course of a time as short as an hour. And then consider the fact that most of these experiments happen on the scales of days, if not weeks. This leads us into our question about the computer processing power and what kind of processing that we use to take in and analyze these signals. For the analysis step, where we take the signal from the detector into a system that gathers it and then puts it on a computer, we use what we call a data acquisition system, or a DAC for short. This is one of those data acquisition systems. This has 32 input channels, so it can take in 32 analog signals, and then it has a processing speed of 125 megasamples per second. So that means that for each of those 32 channels, it can take in and read a signal, and it can collect a data point once every 8 nanoseconds. And that may sound super fast, and it is super fast. This is a super expensive advanced piece of equipment. But once again, going back to the barium fluoride crystals, which can produce peaks that are less than a nanosecond wide, taking data once every 8 nanoseconds is going to completely miss most of those peaks. So even this board is not enough processing power to pick up the signals that we want to be able to read. For that, you have to have an even more advanced digitizer than this, which takes in the analog signal, runs some sort of algorithm or filter on the signal that you program into the board, and then spits out whatever parameters or results that you want, whether that be a raw signal or the energies of all the peaks that you see or the timing of all the peaks that you see. It has to be able to take in that analog signal, analyze it with enough granularity to pick out what you want, and then spit that out to the computer in some sort of list of data, which we can then go through and process. So you would need a digitizer that is advanced enough to take in that amount of data and take data points, multiple data points every nanosecond, to even be close enough to seeing what you want to see from barium fluoride. And those do exist, but let me tell you, they're very expensive, and they do not make them like this with 32 channels per digitizer. You would find one that maybe had 2 channels or maybe 4 channels if you were lucky. So yes, this detection technology has been around for almost 100 years now. The idea of a scintillator catching a particle, producing light, and then that light being amplified by a photomultiplier That is not new. This is old technology, but it still works. Thank you for these very insightful questions, and please keep the questions coming and let me know if there's anything else that you want to see or you want to know more about from this video.